Welcome to the lesson on work. Work is the thing you get when a force acts over a distance, and it follows the very simple formula: work equals F dot D, and in our physics that's pretty much F times D in most cases. And work has a very close relationship to energy, in that when you do work on an object, you are basically taking one type of energy and transforming it into another. So if you walked up to a car that was stalled and you were pushing that car along, the chemical energy in your muscles is becoming kinetic energy in the car. So the unit of work is joules. So looking at this formula here, you can see that if I have an object and I'm applying a force to it, the longer distance that this object moves down whilst I'm applying the force to it, the more work I will have done on it and the more energy I will have put into it. And you can see this in real life. If you were throwing a hammer off a ladder to your mate down below, and the hammer sailed off the ladder and your mate is just a little bit below, he'll probably catch that, no worries. Because although the force on the hammer is gravity, which is quite large, the distance it has travelled is actually quite low. Therefore the work on the hammer is low and the change in energy is also low. But if the ladder was very, very high and you tossed that hammer off and your mate was down here and that hammer's got all this distance to fall, all of a sudden the distance is very high. The work on the hammer by gravity is very high and the change in energy of the hammer is very high, so it'll have a very high velocity when it reaches your friend. My first job was mowing lawns. Let's have a look at how the work applied to a lawnmower changes its velocity. So I have a lawnmower here with a mass of 30 kilograms. And we'll apply a force to the right of 75 newtons, and we'll just emphasize that this lawnmower is on the grass. So let's draw in all forces. We'll do it in blue. We have the weight force, which is mg, or in this case 300 newtons, and then the normal force, which we don't know but we can work out. The lawnmower is not going to float off the grass or into the grass, therefore the normal force must cancel out the weight force, because these are the only two forces with vertical components in this diagram. So the normal force is also 300 newtons. So for the purposes of this question, we can pretty much ignore these two forces, but I'll leave them in. So we ask, what is the work? Say that this force is applied for a distance of 2 meters. Then work is equal to F dot D, or force times distance, and that's equal to 75 times 2, or 150 joules. If this lawnmower started from rest, U equals 0. Let's work out the final velocity. First of all, we say, okay, the initial kinetic energy was 0, because Ek equals a half mv squared, and if v equals 0, as it did over here, u being the initial velocity, then the kinetic energy would also equal 0. So the initial kinetic energy is 0, and the final kinetic energy equals the initial kinetic energy plus the work that was put into that lawnmower. So that's 0 plus 150. So the kinetic energy at the end is 150 joules, and we know that must be equal to, according to this formula over here, 1/2 m, which is 30, v squared. So multiplying both sides of this equation by 2, 300 equals 30 v squared, 10 equals v squared, v equals 3.16 meters per second. But that's a very simplistic way of looking at this problem. Let's assume that the lawnmower does not start from rest. So the same amount of work is being done. This is still correct. But if the initial velocity were, say, 2 meters a second, then the initial kinetic energy is equal to a half 30 2 squared, which is equal to 15 times 2 squared, which is equal to 60 joules. And the final kinetic energy is equal to the kinetic energy it had at the start plus the work. So that's 150 plus 60. Therefore, the lawnmower must have 210 joules by the time it has run along the ground 2 meters. And 210 joules must equal a half 30 v squared according to this equation up here. Therefore, for 20 over 30 equals v squared, and I have that down here as v equals around 3.74 meters per second. Let's test this with our constant acceleration formulas. So I'll take this portion here and I'll scale it down, move it over, and we'll use just the information we said at the start. So we said u, the initial velocity, was equal to 2. V is a mystery. The displacement was equal to 2. And the acceleration we can figure out. So we know that F equals ma. Therefore, 75 equals 30a, 75 newtons accelerating here. So 75 on 30 equals a. A is equal to, what's this, 2.5. So here are our variables. We have u, we have s, and we have a. So let's use this formula here. V squared equals u squared plus 2as. V squared, which we want to find out, is equal to 2 squared, that's 4, plus 2, 2.5, 2. V squared is equal to 4 plus 10. V squared equals 14. And I have here V around about equals 3.74. And of course, if V squared were equal to 16, V would equal to 4. So this answer looks about right. Let's look what happens when you have a force that's being applied in a different direction than the movement, because things get very difficult when that is the case. Okay, new lawnmower. Same weight. But now it's more true to life. We have a handle here, and the force is being applied down the handle. So I'm going to draw the force here, acting from the center of the object in this direction, just to make sure there's no mistake. And that force is equal to 160 newtons, and this lawnmower again is sitting on the grass. So first of all, we draw in all the forces. mg, or 300 newtons. Now, I'll add some more detail to this. This force on the handle, we'll say, is acting at 60 degrees below the horizontal. Therefore, this angle here must be 30 degrees, because That's 90 degrees. That's a little unclear, hang on. 30 degrees. We'll break this force up into its horizontal and vertical components now. So this component of this force is equal to 160 sine, since it's opposite the angle, 30 degrees, which is equal to 80 newtons. And there is also a vertical component to that same force, and that's given by 160 cos 30, which comes to, what's this? 138.6 newtons. So we can pretty much ignore this force now, since we've resolved it into its vertical and horizontal components. Now we know this lawnmower is not going to fly off the grass, nor sink into the grass. Therefore, the normal force has to balance out the vertical component of the pushing force on the handle and the weight force. So the normal force has to be equal to the weight force, or 300 newtons, plus 138.6. If this weren't the case, if the normal force were too small, this force here and this force here would pull the lawnmower into the grass. And if the normal force were greater than this, then the net force vertically on the object would move it up like that. So it has to just balance out the gravity force and the vertical component of the pushing force. And that comes to 438.6 newtons. The main point here is to realise that the vertical forces sum to 0. This lawnmower is only experiencing a horizontal acceleration due to this force down here. So now we've got this lawnmower, and a very simplistic view of it is it's just got this 80 newtons there. That is the net force. F dot D is the work done by the force on the handle to the lawnmower. So we'd say work is equal to F dot D. I said before, in most cases, this is the same as force times the distance. But that's only true when the force is acting in the same direction as the distance. In this case here, the force is not. The force is acting down like that, and the distance is over here. So in order to discover the real work done by the force of the handle on the lawnmower, we have to only consider the component of the force acting in the direction of the distance. So if the lawnmower is moving 2 meters in this direction, we look at this force here and we say, okay, this is the component of that force acting in that direction. So work equals F dot D equals 80 newtons times 2. That's 160 joules. And so the kinetic energy after those 2 meters is equal to 160 joules if this lawnmower started from rest, which it did. Let's figure out the velocity. 160 equals a half 30 v squared. 160 multiplied by 2, 320 equals 30 v squared. 320 divided by 10, 32 equals 3v squared. 32 divided by 3, 10 and 2/3 equals v squared. V is going to around about equal, gosh, what is this? 3.2. Check that on your calculator. So the most important thing to remember is that for work to be done, you need a force and a distance. Work often adds kinetic energy to an object, and you should only count the force, the component of the force, that's acting in the direction to the distance that the object is moving.